Hey guys, Itchy Beard McQuaid here. Oh, it really is quite itchy. Coming to you, lost my train of thought, awesome. Coming to you today with another video on action potential, hopefully making it more clear than last time. So we'll make this one part 2. If it seems like I've already written there, it's because I did do all this video beforehand, except I did it as a time lapse. So it doesn't really make any sense because I'm just going real fast. Anyway, so we had a look at the movement of the molecules or the ions at the actual membrane, but we didn't actually really go very much detail into this magnificent graph, which tells us about the membrane potential that occurs and also results in why we get to call it an electrical kind of signal. Ew, big swallow, gross. So before there's an action potential, the membrane always sits at -70 here. So just sitting there, just chilling, we be chilling. And for an action potential to occur, it has to reach the threshold of -55 millivolts, which means there has to be a slight change in the membrane potential. If it doesn't reach this threshold, no action potential occurs. But once it reaches this threshold, what that does is that opens the sodium gates. And once the sodium gates have opened, that's called depolarization. So essentially, the sodium then floods into the cell. So that's all that happens. The sodium floods from the outside inside because it wants to reach equilibrium, which means a heap of sodium then goes in, and potential rises up to around about +30 millivolts. So once all the sodium is now inside the cell, what happens there is that triggers then the next section, which is repolarization, and the potassium gates then open, and then the potassium then floods out of the cell. So that continues, which tries to get the membrane potential back to the way it was. So eventually here, all the potassium has left the cell, and all we've got is sodium inside the cell and potassium outside the cell, which, if you remember back to here, or back to action potential, is the exact opposite of what we need to start off with. We need sodium outside, potassium inside. Again, up is out, down is in. Alright, so it comes down here, it reaches this point here, and the body goes, "Oopie daisies, they're the wrong way round." I don't think the brain sounds that dumb, but let's just go with it. Alright, so what happens is we have these specialized pumps called sodium-potassium pumps. Now the back of my head's real itchy. Maybe I have lice. That could be gross. Anyway, and what this pump does is it pumps the sodium out and the potassium back in, reaching it back to this initial point where we have all sodium outside, all sodium inside. So what that does, but as a result, let me have one train of thought for once, it dips below that 70 millivolts. So it drips down until eventually all of the sodium is being pumped out and all of the potassium is being pumped back in, and it reaches back here 70 millivolts. Now, during this time of hyperpolarization, which means it's dipped below the initial membrane potential, you cannot have another action potential. You have to wait till it reaches back here until you can have another action potential. Now, this process from initiating an action potential to being able to initiate another one in an average human is about 3 milliseconds. I think I said beforehand 30. Well, I was off by a magnitude of 10, which doesn't seem like much, 30 to 3, but in the case of our body, that's really slow, and we need it as quick as possible. Because think about how doing that there, sending a heap of firing signals. All right. Now, what this does is it means you can't have a continual action potential, so a continual stimulation, which depending on which organ you are trying to stimulate, whether it be a muscle, if it's continual stimulation of the muscle, you get tetanus, which is essentially just a constant contraction of the muscle, or if you're signaling a gland to release certain hormones, if you don't have this hyperpolarization part, and you just do have a consistent action potential, all that gland is going to do is release its hormone or release its substance that the body has told it what to do. Now, with these ones here, you can actually train this to be less, because there have been some studies that have shown that professional athletes have the smallest hyperpolarization period, which means that they're able to have another action potential much quicker than the average Joe Blow off the street, whether that's due to their genetics, their anatomy and physiology, or due to their training, or a combination of all three coming together. I don't know, I just kind of quickly Googled it, and as all good research, I looked at the title, and I was like, that's good enough, so it's not. Alright, so, yeah, hopefully this, combined with my other gross drawing that I did back on the other page, hopefully you bring those two together and they're not super confusing. If they are super confusing, I'll be adding another really good video, unless it's the same one, I don't know, to this thingy here. But again, if you want to go through it again, just down the bottom here, just push this all the way back to the start, and just watch this again. And if not, I will see you in the next video. I don't know if that was any good. Oh well, we're doing one take only.